Okay, class, so we're going to take a look at the strong base weak acid titration. We're going to look at part C here in our notes. Now remember from the last part that we already had in our beaker we were titrating into, we already figured out from the previous part that we had a total of 5 millimoles, if you remember from class, 5 millimoles of the acid. So we have 5.0 millimoles of the acid. I'm just going to use HA to keep that short. And we're adding hydroxide ions, a strong base. And so we need to right now calculate our millimoles of our base that we are adding. So we're going to say 25.0 milliliters times 0.10 molar for the sodium hydroxide. And that's going to give me 2.5 millimoles of hydroxide ions that we're adding into this. I'm also going to go ahead and do my V total calculation. So for V total on part C, we're got 25.0 milliliters plus we already had a total of 50 milliliters in the flask. So we have a total of 75.0 milliliters for the V total when we need that later. So let's do our stoichiometry first. We're going to take our OH ion from the titrant and we're going to react it with the acid that is in the flask. So HA, and this is going to form water and A minus. And it's okay with me if you use that to shorten it up, just I'm kind of short on space here. But of course, this is acetic acid that we're using here. Now, the reason we need to use millimoles in this part of the problem is because we have a volume change here, so we have to recalculate the concentration at the end. But we just figured out we had 2.5 millimoles of the base. And the acid in the beaker from the beginning, we have 5 millimoles, 5.0 millimoles. Now, when you do your shift, remember you're going to shift all of the OH is going to get consumed. The smaller number gets consumed, so minus 2.5, minus 2.5, and then over here, plus 2.5. And these are millimoles, of course. So we're going to have none of the hydroxide remaining at the end. We'll have 2.5 millimoles of the acid, and we're going to have 2.5 millimoles of this conjugate base. Now, since these are the same millimoles, we know that we're going to have the concentration of HA and the concentration of A minus are going to be the same. So when you plug into the Henderson-Hasselbalch equation, which is what we're going to do next, you're going to have pH equals the pKa. This is what we call halfway to the equivalence point. Halfway point to the equivalence point, because these are equal molar here. So if you go ahead and get your new concentration, concentration of HA in this case is going to be equal to the concentration of A minus, which is 2.5 millimole divided by the 75.0 milliliters. And of course, we kind of know what's going to happen here, but just to kind of keep the continuity of the problems, so 2.5 divided by 75, we have our concentration is going to be 0.033 molar. So plug it into Henderson-Hasselbalch, pH equals the pKa plus the log of the base over the acid. So here we're going to have 0.033 over 0.033. So of course that's going to give you log of 1, which is 0. So we have pH equal to the pKa. So for this problem, the answer, the pH of the solution is going to be 4.74. Okay. All right, in part D, we're adding 50 milliliters total to our solution. So let's do our millimole calculation again. So we have 50.0 milliliters times 0.10 molar. So 50 times 0.1 is going to give you 5.0 millimole of hydroxide added. So our V total here is going to be equal to 50 plus 50, which is going to give us a V total. Let me try to separate this out. So the V total for this part is going to be 100.0 milliliters for later. We'll need that. And we're going to do the stoichiometry. OH plus the weak acid is going to form water and A minus. So let's ice our problem. ICE. And we have none of the A minus at the beginning, but we have 5.0 millimoles of OH, and we have 5.0 millimole of HA. So we subtract the smallest amount, minus 5, plus 5. So we have 0, 0, and we have 5.0 millimole. Now, at this particular point in this titration, we have none of the OH or HA, but we do have A minus. And remember, this is a conjugate base. Okay, so we're going to have to do something with this. This is where, in my opinion, this is the trickier part of the titrations, because in our notes here, I want you to write the pH at the equivalence point. And this is the equivalence point when you have the OH and the acid components are equal molar. The pH of the equivalence point of a weak acid, strong base titration is always going to be greater than 7. And it's due to the basicity of the conjugate base that we have here. Okay, conjugate base of this acid. All right, so at this point, what you have to do is an equilibrium problem. You cannot use Henderson-Hasselbalch. So what you have to do is take what we have that's remaining. We're going to go ahead and find the concentration of A minus. So the concentration of A minus is 5.0 millimoles divided by the V total, 100.0 milliliters. And that's going to give me 0.050 molar of A minus. All right, so here's what's going to happen, y'all. Interesting thing. This is the strongest base that's present, so we're going to react him, A minus. He's going to react with the only thing he can, which is water. Water is the only other thing there that he really can react with. And this is going to form an equilibrium. Now keep in mind, this is a conjugate base. So bases are proton acceptors. It's going to pull a hydrogen off of the water, and it's going to leave behind a hydroxide, and it's going to form HA. Now, if you notice, this equation here is going to look exactly like the previous equation, but it's flipped around. That's going to always be true at this point in our titration. But this is an equilibrium problem, not a stoichiometry problem. So we're going to ice this. So from this, we're going to pull down the 0.05. And we're going to have none and none, 0, 0, because that's from over here. Now we're going to define our shift in terms of x, minus x, plus x, plus x. Now since we have an initial amount present, and this is a weak base, we can neglect x, so 0.50, x, and x. Now since this is a base, we need a Kb, and we have Ka. So we got to find our Kb by taking our Kw divided by Ka. Now the Kb is going to be 1 times 10 to the negative 14 divided by the Ka, which was 1.8 times 10 to the negative 5th. That's going to give me 5.6 times 10 to the negative 10. I'm going to mark this part E out for now because I'm running out of room. Okay. Now at this point, you're going to do Kb equals concentration of OH times concentration of HA over A minus. You're going to plug in your values. 5.6 times 10 to the negative 10 equals x squared over 0.050